Hi, hello everyone. As I already said, I'm a lawyer, but also I'm a software developer. A colleague of mine was supposed to be here today. Actually, Martin Rabanser, technology and business consultant working for Neutech Park, both in Italy. Unfortunately, he's sick today, but he's recovering. Is not 100% yet, so he's attending today. But I will do the presentation. Then we both will be available for the Q&A session. For those of you who attended yesterday's presentation, some information about the UNIRO project were already given by Marta's presentation, and some general context about SBOM generation in Yocto has been given in Joshua's presentation, also in Michael's presentations. So I will start from that, and so basically the context. So UNIRO project, as Marta said yesterday, is an Eclipse Foundation project. It's Yocto based. It's an all scenario OS platform, meaning that it's a Yocto based distribution that can be built for a large number of target machines with different kernels. We have more or less a build matrix counting all images and of more than 100 targets. So it's kind of a challenging project for compliance, because we wanted to integrate compliance with the same philosophy as in continuous development, continuous integration. So we wanted to have a continuous compliance process, and to do that we developed a dedicated tool chain. The main partners for this project, that is a sub-project of UNIRO, are Neutech Park, a science and technology park based in Bolzano, South Tyrol, Italy, and Array, that is the law firm I'm partner of, that is specialized in IT law and especially in open source compliance. So we based our work on existing open source tools. For those of you who know them, Fossology, Scan Code. But we needed to develop a set of custom tools, Aliens for Friends, Teamfolet, and Aliens for Friends dashboard. I may give you some details later on. Basically, we started from UNIRO, but the toolchain could be, in theory, implemented in any Yocto-based project, especially in projects where you have multiple targets and you have to manage a bit of complexity. And thanks also to an outstanding audit team working on Fossology, we managed to release 100% coverage of source software for the upcoming UNIRO release, meaning that we have reviewed every single source files used to build each of the target images available in the UNIRO project. How did we do that? Of course, there was a lot of hard work, but we also did that in the open source way. So we reuse a lot the Debian community work, because the Debian project mandates for a machine readable copyright file for each package. So basically, we reuse that work whenever we found a good match in the Debian distribution of the components we found in the UNIRO project, all done automatically. So this is the endpoint of our work. It's a dashboard where you can monitor the overall progress of the audit work, license that have been audited, and also the details for each single package. So if you wanted to explore, please download the slides and you can click on the link and we see the dashboard, the current status. Okay, this is what we've done so far, but now we want more. So this presentation is more about version 2.0 of our compliance toolchain that for now is still a work in progress. We have some proof of concepts that I will present in a minute. So mainly we wanted to use a graph database to represent the software bill of materials. One questions at yesterday's Michael presentation was about how do we consume an SPDX SBOM, because okay, in theory it's human readable, but in practice it's not. It's too much data. So we plan to use a graph database both to show the data and to process the data via graph queries. Why do we need graph queries? Because we want to do software composition analysis, dependency analysis, and automated license incompatibility checks all through queries. To do that, we needed to map all license metadata that we already have from our audit team, from Debian community, as explained before. Possibly in the future, we may reuse data from clearly defined projects and other shared data sources. That's all in the openly available, so everyone can consume that. So we map all those metadata we have on upstream source packages down to binary files. So we wanted to do a file level mapping of licenses. And this because we want to find a way to automatically combine different inbound and outbound licenses and check their compatibility. We are currently working on a proof of concept that we show you in a minute. This is the new version of the dashboard that will include also a graph database presentation. It's already deployed, even if it's really work in progress. So don't trust it. It will probably crash many times, but it's already deployed here. And some background. So why do we need all this? Okay, this is the Yocto workflow, very simplified. Probably all of you already know it. So we have a lot of upstream sources. Many recipes have only one upstream sources, but there are a lot of recipes that combine multiple upstream sources together. And in any case, there is the downstream patches applied by the recipe and coming from a Yocto layer, and that is another upstream source for the recipe. And then everything is combined together, downloaded, unpacked in workdir, compiled, and installed in the image. What's the problem here for on our side as compliance experts? So we need to know the license of all this. And if you look into each upstream component, we find a lot of diversity. So there are components that have only one license, but there are very few of them. Most of them have many licenses inside. Some of them may be conflicting. Many upstream sources may be combined together, and the combination may change the outcome. So the outbound license. And sometimes we find also bad things like binary blobs without a clear license and so on. The problem is that, the binary file that is generated has no clear identity because, for instance, you have a recipe with a lot of licenses, but you don't know which license applies to that particular binary because probably from one recipe, you build 1, 2, 3 binaries and they get different licenses, as I'll show you in a minute. And the final problem is that the image, we can find strange things that could create some issues, some legal issues when you market the product, and that will come with a cost that we want to avoid, or at least we want to minimize the risk. A bit of a legal background. Basically, what you usually do when you develop a new application or anything, you take some code from third parties. That code has its own conditions, and conditions of software you are reusing is called inbound. So all components that you're fetching in Yocto are inbound components and have inbound licenses. The conditions software you are distributing outside is called outbound. And if software contains a portion of other software, it is a derivative. So basically, a Yocto generated image is a derivative of a whole bunch of source components with their own inbound license. So derivative software requires that all conditions are complied with. When this is not possible, we have unlicensed incompatibility. So you cannot combine the software. Or sometimes you have only limited choices, or possibly only one license. So we have two possible problems here: inbound incompatibility or outbound incompatibility. So you have two components here, A and B. They need to be combined together, and this is a derivative work. So it may be that the inbound license of both components is okay with the outbound license, but the outbound license is not okay with the inbound, or the other way around, that there is a license of an inbound component that it is not okay with the outbound license. And this is the kind of problem we need to spot automatically and obviously solve before the product is marketed. So we need to find the relationship with third-party upstream code inbound, find under which license each inbound upstream code component is, and therefore we have to get a list of inbound licenses, find if there is a possible combination of them, and match this combination with the desired outbound license, or at least get the options we have for the outbound license. And this holds for each artifact. This is not something for the whole image. This is not something for, the single package, because a single package may have different files with different licenses. And so we need to do that for each single binary file. So coming to our graph database, we start with a simple example, the GPG Made Easy package. In our case, we have 3 binaries coming from that package. And the first binary, as this situation, we have 2 MIT sources. As probably you already know, MIT is a very permissive license with no issues whatsoever. And here we have some copyleft licenses, GPL family licenses. And we have also weird combination. We have a file that is under an option, dual license, GPL2 or GPL3 or later, and another file with GPL3 or later. So we need to conclude the license of this binary file. So this is the upstream yellow one. The yellow dots, the purple dots are the local source files in the workdir, and this is the binary file generated by the recipe. So always sticking to the GPGME example, we have another binary file, but here the licenses are different. We have MIT, but we have LGPL 2.1 or later. So we have a different situation. And then we have a third binary. This is kind of a problem, because it's not humanly readable. We are working on finding some solution to browse this graph, but again, it's not it's very difficult to do that without automating things. So what do we think for solving this problem? So we thought about some play role games when you have multiple cards fighting against each other, and each card has some characteristics, and you need to decide who wins. You can have many strange licenses out there. So for instance, this is it's not a joke, because actually there was a kind of a Che Guevara license inside the zlib package until some time ago. It was kind of a joke, but it was a license saying that you cannot use the software if you're a user of Che Guevara paraphernalia or something. It was a kind of a joke, but there were actually some companies that were prohibiting people from using software containing this kind of strange licenses, whatever. So we need to decide who wins in this license battle. Yeah, this is just tentative, just to explain the logic we are using in our proof of concept. So we needed to define a set of rules. So we need that if in a battle between GPL3 or later and LGPL3 or later, according to Free Software Foundation, the result is GPL3 or later. And yeah, we have many other possibilities. For instance, LGPL3 against GPL2, there is no winner here. This is an invalid combination. So here we have a license incompatibility. In other cases, you may have strange results because, for instance, if you have LGPL3 and MPL2, there is where the result that you can release the main software component under a dual license scheme. So it's very complex, but yeah, we think that in this way we can solve the problem we were talking about before. If you want to know where do we take this information, mainly we take, for instance, this is the website of the Free Software Foundation. There is an interesting license compatibility matrix. Then we, I don't know, from the Mozilla website, we have yes, this document that explains how to combine differently licensed artifacts, and then yeah, for Apache license, we have the Apache Foundation website. So the idea is basically to yeah, write down here the source of this rule, because of course in the legal field everything could be debatable, so you must know who decided that rule, and if you like it, you keep it. If you don't like it, maybe you use your own set of rules. So rules in action. If there is time, I will show you also that live later on. So we have the inbound licenses. Remember the first example. So we have MIT, we have GPL2 or LGPL3, and we have GPL3 here. So we take just unique values, and we get this. Here we have an OR. So basically this is an option, and we need to explore all possible options. So we calculate the Cartesian product of this list, and so we get a first combination, and then in the next slide we have the other combination, and then we apply all the rules that we think may fit. So GPL2 wins over MIT, GPL3 wins over MIT, GPL3 wins over GPL2. So the final result of this combination is GPL3 or later. Same here, you have GPL3 that wins over LGPL3, GPL3 that wins over MIT, LGPL3 that wins over MIT, and the result is still GPL3. So both combinations, both alternative combinations, lead to the same result, that is GPL3 or later. So we know that this file is GPL3 or later. Of course, if you apply the same algorithm to this file, it will conclude that this file is LGPL 2.1 or later. I may show you maybe here. No, this one. Okay, so if we execute this query, we get the result that I show you. That I just show you. If we look for the license of this other binary, we see that the outbound license LGPL 2.1 or later. And yeah, so basically, yeah, what we were planning to do is to build a database of rules in order to solve all these kind of conflicts, and to be able to automatically conclude the license for each binary that is included in your final image. And of course, to check if there are license incompatibilities, as I showed you before, between inbound and outbound licenses. And just one footnote. In the past, the approach to compliance of many corporations was about blacklisting some open source licenses. Now it's there are still corporations that have blacklists, but since when you have an operating system distribution, it's very difficult to blacklist some licenses. You cannot blacklist GPL2, for instance. So the thing is, you should not focus on blacklisting some licenses. You should focus on avoiding license incompatibilities. So what you are distributing is compliant with all licenses. There is no incompatibility, no inbound or outbound compatibility. So you have the right to distribute the open source components that you are using. That said, just a final note on how we are collecting the required data on Yocto's side. So we map upstream source files to local workdir source files and down to binary files. So partially we consume metadata already available from Yocto. Yesterday Joshua talked about this create the SPDX class that does a great job in providing such metadata in standard format. Then we cover the last missing bit. So we fetch upstream source packages, including Yocto layers that we treat as upstream sources because they contain code, patches, scripts, and so on. So we fetch them separately, and we collect path and SHA-1 checksum and for every file, and then we map everything to local workdir source files. And then, of course, thanks to the debug sources information, we map everything to binary files. Currently, we are using a post-mortem Python script leveraging the tinfoil library of debug. It's useful to do software composition analysis, but the natural place to do that would be in some class of Yocto, and probably in the create the SPDX BBD class.